I start? Thanks. So we're team Datasset. I'm Klaas, and together with Michael and Peter, I'm doing a PhD in analytics at Leuven University. We have Andreas, who is working as a data scientist at a telco company, and Joren, our domain expert, who is a doctor and has studied tropical diseases, exactly. Domain expert, clearly. Yep. So this is the team. Mosquitoes must die was our tagline from the start. Next slide, please. What problem did we want to tackle from the beginning? We wanted to do some predictive modeling of dengue evolution in Sri Lanka. Now, why Sri Lanka is a thing you might ask instantly, and that's my cue to pass the mic to our domain expert.
So Sri Lanka has seen a major decrease in the number of dengue cases, and more than other countries in recent years, since a very significant increase since 2009. And probably it's due to the importing of other serotypes. The other thing is that there's been climate change, change in precipitation, which makes the cyclic presence of dengue less predictable. So that's why it would be nice to have predictive value.
So a big thank you to the people who prepared the data. I believe your contribution to this whole hackathon has been invaluable. Without the preparation, we wouldn't have been able to build all these models. So what was our approach? As a first step, we wanted to do some visualization, what is going on at the province level in Sri Lanka. The second step was doing some time series modeling, how many people were diagnosed when and where, in which province, in which month. The third step was understanding the business. Can we leverage this expert knowledge in bringing more covariates in our time series model? So this is a visualization of Sri Lanka. Can you press the play button? Where this is monthly dengue outbreaks. So it gave us already quite a good idea, and these insights are really valuable. The really dark zone here, this is the capital of Sri Lanka, where there is also a very large population density. The second step was the time series modeling per province. And we see here two provinces, one on the left and one on the right. The x-axis are the months, and the y-axis are the number of cases of dengue. And for example, on the left, we see a big trend, and there's also some seasonality. So our insight here was that interventions at different places might be required at different times. Then we built an ARIMA model, and we used several data sets for that. For example, the historic number of dengue cases per province, some climate data, and some data from the World Bank, for example, development indicators, sanitation, and also water supply, exactly. We achieved mean average percentage error of 36%, which is quite large, so we have very much room for improvement. For out-of-time validation, so we train our models, for example, from January 2010 until January 2013, and then predict February 2014, and so on. Lots of room for improvement, okay. And we were quite happy, hopeful, to see that our model or our predictions were consistent over the different provinces. It wasn't the case that for one province, for example, we were completely off, and for the other we were completely under-predicting. So even though we had a mean average percentage error of 36%, the model was still consistent. Now, how does this fit in the bigger picture?
Yeah, this is a bit of theoretical background on what an epidemic looks like. You see the rise and fall of the number of cases over time. And the top graph shows what we are doing right now. So we measure the amount of cases that come into the hospital that have fever, that are diagnosed. We alert the authorities, and we put in measures, mainly vector control. But as you see, there's a lag between the the reporting and the input of measures, and the green bar is the number of avoided cases. What we are aiming for is earlier detection and earlier implementation of measures, so we can increase the number of preventable cases. The downside of early detection and early implementation is that you might detect bumps, so false positives, as we've seen in the other model, lots of red and not so many epidemics, and you could over implement your measures, actually.
Mm-hmm. And if nothing else works, if we still have these large mean average percentage errors, we can still build a wall to keep the mosquitoes out. So this was it for Team Dataset. We still have a small video. Some two very important things I also needed to say was this whole analysis, the presentation and everything is completely reproducible. Everything has been done in R, and this is an R Markdown presentation. And we linked everything to GitHub, so available to all. And we started from scratch completely. We did a Git init yesterday at 3 p.m. So yeah, this is where we got. And now we still have the demo. This is our dengue dashboard. So this is a Shiny app in R. You can select cities. You see the evolution throughout time. We have the map I showed earlier in the presentation, and also some the other map on the left. We can choose whether we want to display the time series according to relative numbers or absolute numbers, depending on the population density. And you can also select the days and so on. Yeah. Thank you.